imagine a world where motion is absolute, where the movement of objects is tied to a fixed, universal reference point. Before the 17th century, this was how people thought about motion. Then came Galileo Galilei and Sir Isaac Newton, revolutionizing our understanding with the principles of relativity. But what does this mean, and why does it matter today? Imagine you are this cat juggling on a smoothly moving train. To you, the apple seems to go straight up and down.
But look at it from outside. The train is moving, so the apple still falls straight down to the cat. That's Galilean-Newtoninan relativity. By now, we understand that physics is concerned with the motion of objects and the quantitative analysis of that motion. But this can be tricky business if you really think about the fact that everything is in constant motion. When we say that a car is moving at 100 kilometers per hour on the freeway, we are ignoring the fact that the surface of the Earth is rotating around the center at about 1,700 kilometers per hour at the equator. Earth is also moving around the Sun at around 30 kilometers per second. So it's not completely wrong today that the car is actually moving with this incredible speed as well, meaning that in a certain context, there's practically no difference between flying in a plane and sitting still in terms of absolute velocity.
Galilean-Newtonian relativity, also known as Newtonian relativity, is a fundamental principle in classical physics that describes how the laws of motion appear the same in all inertial frames of reference. This means that experiments conducted within a system moving at a constant velocity will yield the same results as those conducted in a stationary system. This seemingly simple concept has profound implications for our understanding of motion and the universe.
It means the laws of physics are the same for everyone moving at a constant speed. No matter how fast they are going, it's all about relative motion.
This simple idea, while not perfect at super high speed, is a crucial building block for understanding how things move around us.
Galilean relativity.
Galileo first proposed that motion is relative. If you're inside a moving ship with no windows, can you tell whether the ship is moving at a constant speed or is stationary? Without external reference points, the answer is no. This idea, known as Galilean relativity, states that the laws of physics are the same in all inertial or non-accelerating frames of reference.
For a sailor traveling at a constant speed in a straight line, cannonball drops at the top of the ship, falls straight down. The observer, however, both the ball and the ship are moving forward, and so the ball is seen to following. This means dropping something can't tell you if you're moving. It looks the same to you either way as long as you're undergoing the uniform motion.
Sir Isaac Newton expanded on Galileo's idea with his famous laws of motion. Newtonian mechanics tell us that the objects move according to these laws, regardless of the observed frame of reference. One of his K equation, force is equal to mass times acceleration, applies equally whether you're on a moving train or standing still.
Consider two cars moving at 6 kilometers per hour in the same direction. If you observe one car from the other, it appears stationary, even though both are moving fast relative to the road. This is Galilean relativity in action.
Galilean and Newtonian relativity form the foundation of classical mechanics, which engineers and scientists still use today. From designing bridges to predicting planetary orbits, this principle guides our understanding of motion. Even Albert Einstein's theory of relativity builds on Newton's work, proving that science is an ever-evolving journey.
Galilean-Newtonian relativity helps us understand the motion of everything from rolling balls to spacecrafts. Next time you're on a moving train or in a car, think about how your perception of motion depends on your frame reference. Physics is all around us, so stay curious,